Please go on.
Okay, thank you very much. First of all, I wish to thank the organizers for giving me the opportunity to speak here. So initially, when Raghu asked me to give a presentation at ICTS, I thought that I should be talking about string field theory, given that there are great string theorists in the audience. But at the same time, I realized that there are also other condensed matter physicists and mathematical scientists at the center. So I should be talking about a topic which might be of common interest to people outside of just string theory community. And that's the reason why I decided to talk about this topic, bootstrapping the physics at finite temperature. Okay. This is based on several works that I've been involved in for the past few years, and indeed, in a month or two, there will be another paper out. Um, Before jumping into physics, I wish to give an introduction to a song, which was actually recommended to me by Igor Klebanov when I was organizing a workshop at Princeton named Positivity. The name of the song is Accentuate the Positive. It's a song written in actually, I guess, 1943 rather than 1945. It's a very nice song, and it has very beautiful lyrics. Okay, so let me share with you some lyrics. It says, you got to accentuate the positive so they know that positivity is something important. Eliminate the negative. So they know that, when positivity is violated, your physics goes wrong. And they're also talking about maximizing and minimizing something. So I think this is an evidence that musicians in the 40s, 1940s, already knew about Bootstrap. So today, I want to tell you about how the physicists' realization of these lyrics is like in the case of physics at finite temperature. So we can ask the question, where is positivity in physics? Say we have an observable O. We are going to do some measurement of it. Okay, it's going to be either classical, quantum, stemmax, stochastic process, or whichever physical process that you want. And the end result is what we typically call expectation value of this observable. And of course, if we measure something observable in real life, it's going to be some real number. And in particular, this result is going to be positive if two things are satisfied. First is that the observable itself has some notion of being positive, and this measurement itself carries some notion of positive. Okay. This sounds very abstract, so let me directly jump into a very simple toy example. Okay. So we are going to consider a function of one real variable x, and the corresponding expectation value we are going to define using this expression. So what are we doing? We are just taking 0 plus 0 dimensional 5-4 theory. Okay. In particular, note that this factor, which is the measure factor, is positive everywhere. For any real x, this is positive. Therefore, if we consider a function p of x, which is positive everywhere, then the corresponding expectation is of course going to be positive. For example, x squared expectation is going to be positive. A more generalized version of this statement is that if you take any real polynomial and take square, the corresponding expectation is going to be positive. And actually, this positivity can be packaged nicely into matrix positivity. So you can easily show that this is equivalent to positivity of matrix M, whose ijth element is given by expectation value of x to the I plus jth power. Okay? Of course, positivity alone is almost a void statement. It just means that we have a positive measure. Nothing gives us specification about this specific measure yet. Uh, the job of Schwinger-Dyson equation is to actually give us about concrete ideas about this specific measure. So what is Schwinger-Dyson equation? It's just saying that if we have total derivative and integrate it, it evaluates to 0. And once you take this type of expression and expand it out, then you are going to soon arrive at relations between different expectations. Okay?
Sorry, just
Actually,
one
this,
second. Sorry to interrupt your very basic question.
mhm,
When you say M is positive, this M is an infinite dimensional matrix.
mhm.
So you converted this positivity statement into an infinite, and you'll explain why this will be useful in what you say.
That's right. So good thing is that if you have a positive definite matrix, infinite dimensional positive definite matrix, any principal submatrix is also going to be positive. Yeah, another way of saying this is that all of the eigenvalues are going to be positive. So if you take only, subset of them, that's still going to be positive.
Thank
Yeah,
you.
so that's what we are going to implement in practice later, very soon. Thank you for the question. So Schwinger-Dyson equation gives linear relation among different expectation values. And now
Can
let's
I just
think
ask?
about, mhm.
Sorry, I think Subrat's question was whether the matrix is infinite dimensional, and I'm not sure if you
It is infinite dimensional.
it is infinite dimensional. Okay.
Yeah, it is infinite dimensional, but in practice, we can only consider a finite part of it. And that still
All right, right.
satisfies the positivity.
Okay, thanks.
Mhm. Thank you. So we are going to now consider a problem. The problem is like the following. We are going to either maximize or minimize, say, x squared expectation value subject to these two constraints, okay, positivity and Schwinger-Dyson equation. Actually, this problem falls under the broad class of something called convex optimization. It's because the space of the candidate expectation values satisfying these two constraints is actually convex. It's basically based on the fact that these matrix elements are all linear, and these relations are also linear in the expectation values. And the particular problem we have here, which involves matrix positivity, is something called semi-definite programming, in short, SDP. Well, I should tell you, SDP is something very standard by now. And by it being standard, what I mean is that there is a built-in function in Mathematica for this. Okay. So here I wrote down very short Mathematica code implementing the problem that I just described. Okay. So here xx is basically expectation value of, x to the power here. And this one imposes Schwinger-Dyson equation. And this cut is the cutoff. I'm going to consider only some principal submetrics of the infinite dimensional matrix where the maximal degree is given by 20. And this matrix is basically the positivity matrix that I told you before. Okay, this is the matrix element. And all we are going to do is to find either minimum or maximum subject to these constraints of, this matrix being positive. And this semi-definite optimization is the Mathematica function implementing SDP. The reason why this problem is very easy is because it's convex optimization. So in the end, all the computer is doing is basically gradient descent. Okay? And the result is the following. This is mean and this is max. You can see that they are very close to each other. They start to differ at this digit. By the way, it takes you less than a second to obtain these numbers from this code. And this is the exact answer expanded to some precision. And you can see that this actually nicely sits in between these two. Let me emphasize that these two things, min and max, actually provides rigorous lower and upper bound on the exact answer. The reason is that we are imposing only what must be true. Okay? We didn't take any approximation. We are just imposing part of what must be true. So the resulting bounds must be rigorous. And this is exactly the philosophy of Bootstrap. We are imposing what must be true and obtain hopefully strong results, strong and rigorous results. Any question about this toy example?
Sorry, just once again, you impose this
Mhm.
Mij is positive,
Mhm.
but what you really need is that the full matrix Mij is positive, and maybe it's obvious, but here you actually impose that a block of that matrix was positive.
That's right.
So is it obvious that this is, maybe it's obvious. Is it obvious that it's the same? That the block
I
has to
mean,
be
it's not the
positive?
same. Of course, positivity of the finite dimensional submatrix is strictly weaker than the positivity of the entire infinite dimensional matrix. But actually, mathematician friends have shown that if you actually increase this cutoff size, then the answer is actually going to converge to the exact value. And we are actually going to see different version of this story in the Ising model very soon.
Right. But the question I was asking was, you impose what must be true. Is it necessary that if Mij as a big matrix is positive, that the small matrix must be positive?
Yes, because another definition of positivity is that if you take the inner product against the one vector and the same vector,
I see. Thanks.
and you can take the 1, 1, 1, 1, and then 0, 0, 0, 0, for example.
Okay. Thank you very much. Yeah, thanks. Yeah.
You're welcome. Okay, so let's take a step back and have a reflection on what we've actually done. What we considered was this path integral given by this measure. Actually, this integral is basically sum over all configurations, where by configuration, what I mean is that we are considering specific value that x can take. And we have this weighting factor, which was in particular positive. So basically what we've just done can be phrased as bootstrapping some ensemble. Okay, we consider ensemble of configurations given by this specific weighting factor. So we can ask if we can bootstrap things like thermal ensemble, and that's what I'm going to tell you today. Okay, and by thermal ensemble, what I mean is that we are basically going to consider physics at finite temperature. And we are going to consider two prototypical examples. First is the good old statistical Ising model on the lattice. This is the model that we all learn in STEM math course. And the second is large N matrix quantum mechanics, which is interesting for various reasons. First is one of those random matrix models, but it's quantum mechanical version. And second is that it's also expected to be dual to string theories or gravity theories. Before jumping into detail, let me give you a brief overview of thermal ensemble. Because there's an ensemble, there should be some notion of space of states or configurations. And there's also going to be notion of Hamiltonian or energy given by H. And thermal ensemble typically means ensemble of states with weighting factor which goes like e to the minus beta h, where beta is the inverse temperature. Well, so what's the difficulty in this very definition? The difficulty typically is that every state, regardless of their energy, contributes at finite temperature. This is in much contrast with zero temperature or infinite beta case, where because beta is infinite at zero temperature, we only need to consider zero, the lowest energy state, in other words, ground states. But unlike this case, if we have finite t, non-zero t, then we actually have to, in principle, go and enumerate all the states in some basis. So that's the reason why practically it might sound very difficult to address this type of question. Well, that's the very reason why people actually have also developed alternative formulations of this thermal ensemble. And we are going to see how Bootstrap provides one such practical definition very soon. So let's directly jump into the Ising model. This is what everyone knows, but let me nonetheless give you the overview. So let's first start with the finite lattice, which is sublattice of the hypercubic lattice. This is, for example, the 2D lattice with 3x3 lattice sites. Okay? And on each lattice site I, we are going to assign spin variable Si, which takes value either +1 or -1. Okay? And the state space is given simply by all possible spin configurations you can have over this finite sublattice. So in this case, there's going to be 2 to the 9 configurations. And by thermal state, we mean something called Gibbs measure. Okay, it's given by a measure. And the measure is given by this partition function. So there's a weighting factor for each state or spin configuration over the entire lattice. And the weighting factor, which we typically also write as minus beta h, is given by this familiar nearest neighbor interaction term. So this is sum over the nearest neighbor pairs. This is the effect of the external magnetic field. And because we are on the finite lattice, we can explicitly carry out the sum over the configurations. So given any function of the spin variables, the corresponding expectation is given by this expression. And this sum is something that we can always perform, at least in theory, over any finite lattice. Well, of course, computationally, the cost grows exponentially as the sublattice, this lattice size grows. And that poses a computational challenge. Conceptual challenge is that, typically it's the infinite lattice, the entire infinite lattice where interesting physics takes place. For example, phase transition. So the question is, how do we even define this type of Gibbs measure on the infinite lattice? Okay? One answer might be that you might want to take it as some limit of the finite lattice case. That is true in some sense, but actually there are subtleties with boundary conditions. It turns out that mathematical physicists back in the 60s, Dobershin, Lanford, and Rule, came up with an alternative definition, which actually holds for infinite lattice. And that is based on the idea that Ising model has local interaction. Okay? Because it has local interaction, they realized that there exists some conditional probability statement which holds true. So DLR said, so this is from these three physicists, given a lattice site I and spin assignments uj, where j is nearest neighbor of I, it does not include I, the probability that Si takes value ui is given by this expression. So here, all I'm saying is that, say you are given nearest neighbor spin assignments, say everything being +1. Then the question is, what is the probability that the spin value at the center takes value, say, -1? Okay. And they realize that that condition probability is given by this expression. So given some specific spin assignments ui and uj's, this is just a number. Okay. And they showed that this is actually equivalent definition for the Gibbs measure on the finite lattice. And then their idea was that, okay, sounds good. We are just going to declare the Gibbs measure on the infinite lattice is any measure on the infinite lattice which satisfy this conditional probability statement. Okay. Well, whenever we face a mathematical definition, I think what we learn in math courses is that we first ask whether such a thing exists, and second is whether such a thing is unique. Of course, both of these answers are no. Indeed, the existence part is true. The answer to uniqueness actually depends on the specific value of the temperature, inverse temperature, and the external magnetic field. In particular, when you set the external magnetic field to be 0, in the high temperature, there is a unique Gibbs measure, while in the low temperature, there's infinitely many Gibbs measures. And the transition point between uniqueness to the infinite case is the mathematically rigorous definition of the phase transition in this case. Okay. So I gave you a very abstract mathematical definition of the Ising model. Okay.
Sorry,
The question is,
formula is derived. What is going into this 1/1 plus x? Like, why is there this 2 and so on? Could you say a few words?
yeah. Basically, it all stems from working explicitly out this weighting factor. So you can actually consider the probability, this conditional probability on any finite lattice. And then actually the probability that specific, I'm going to soon introduce this, okay, so probably this will answer your question. So how do you relate probability to some specific, functions? It turns out that there exists something called indicator function. Okay? So consider this thing. This is 1 if SI is 1. This is 0 if SI is -1. So this is a function which indicates whether your spin value takes value 1. And then the corresponding expectation has the interpretation, the probability of this SI being 1. Okay? If you recall your real analysis course, this is basically the analog of the bump function in the real analysis. So now you can actually compute this thing in the finite lattice case, literally using this. And once you do all of those things, of course, there will be some exponential factors. And if you work it out, you're going to land on this expression. Okay. It's like a 2-page exercise. Yeah. Did that answer your question?
Like naively, I would have thought this probability is just proportional to, one term, because you're fixing UI and all the nearest neighbors. Then
Mhm.
you just get, one term from this weighting factor. Like,
Oh, sorry, but actually the probability, of course, depends on the nearest neighbors because there's this nearest neighbor interaction. Right? So all I'm saying is that, for example, if you're considering ferromagnets, if all of your nearest neighbors are pointing +1, take value +1, then there is a higher probability of the spin at the center also takes value +1.
of course, I'm just saying, in this formula, the left-hand side is fixing UI and UJ both, right?
Oh, that's right. So this is a number given UI and UJ.
Yeah, but why is it naively not just e to the minus beta and just the terms involving those specific spins?
Oh, here we have just UI and UJ. There's nothing more. Yeah, so this UI is the UI here, and this UJ is UJ here.
You have integrated out everything else except these 5 spins.
That's the thing. So that's the reason why DLR observation was powerful. They observed that this type of conditional probability is, respected regardless of the rest of the spin configuration. So in a sense, what they realized was basically a local statement, which is defining the specifics of the Gibbs measure. And they realized that that's exactly given by this conditional probability, and it doesn't depend on the spin assignments outside. Or in other words, as you said, you basically sum over all possible things that can happen outside.
Okay, so that's one way to think about it, that you've summed over everything else except these 5 spins.
That's right.
Okay.
5 spins in the case of 2D. Yeah.
So, sorry, I have a follow-up question to that. So I can see you said with some algebra, one can derive this fact that you integrate out the other spins and you'll get this expression. But the converse seems to be very non-obvious. For instance, using this, you cannot compute the correlation function between a spin and a spin that's 4 sites away. So the fact that this marginal, so using this expression, one cannot compute the correlation function between a spin and a spin which is separated by 4 lattice sites, right? Using just this boxed expression. So it seems
actually,
yeah.
Great question. I'm going to address that very soon. If you can wait for a bit.
Okay. Yeah, so but you're saying that if you give me this marginal probability distribution that completely specifies the big partition function, and that is very non-obvious, but somehow you're saying that's true.
It is also true.
Okay.
Yeah, it is also true. I mean, roughly the idea is that, the very definition of the Ising model is local. So there better be a local way to define the theory. Okay, local way to characterize your measure in terms of probability statement, which cares only about some nearest neighbor configurations. That's roughly the idea.
No, but there might be many partition functions that might give rise to the same marginal probability distribution. Like, how do you know there's a unique, free energy expression for the whole lattice that gives you?
That's good. So good. So
marks, right? I mean, you have this question mark in front of the unique.
Yeah. Yeah. Actually, yeah. Very good. Very good. So if you're on the final lattice, actually, this is along the line of the moment problem. Okay. I think I'm going into much more detail than I initially tried to explain. So there is this moment problem. What's the question? Say you have positive measure and you're given some candidate, moments. How do you know that such a measure actually exists? Actually, the moment problem for the this type of problem is actually completely solved. On the final lattice, if you can actually show that this gives rise to a unique answer all the time. Okay, given specific boundary condition. On the infinite lattice, as I said, the answer may or may not be unique. And that's exactly the interesting part, both mathematically and physically, because that's the transition between different phases.
Can I ask a question, please?
Yes, please.
Yeah. So in terms of this probability distribution that you have written, the local one, is there a formula for the partition function in terms of this?
Not quite, and that's exactly the point. So because, if you actually try to consider this on the infinite thing, of course, this thing and this thing alone, separately, are not going to make sense. Okay, they are going to basically diverge. You sum over infinite many things and you get infinite many terms. So there exist actually limiting procedures where you can actually define this type of thing on the infinite lattice, but that thing actually depends on the boundary condition. There is a way to carry this out systematically, but the great observation by DLR was that one can actually avoid talking about all those things if one simply defines Gibbs measure as any measure satisfying this thing.
Just a follow-up question. I mean, so this is for the Ising model. I mean,
Yes.
suppose I have something like a ON vector model, of Heisenberg type spins. Do you know how to so easily write down something like this?
Good question. So when the number of the degrees of freedom at the local site is finite, and whenever
Yes.
you have only local interactions, actually DLR definition carries through. They actually gave a definition which is more general than just the Ising model case. If in continuous degrees of freedom at a given local site, good question. I actually don't know the answer to that. Maybe it's something that we should look into the math physics literature.
Nice. Okay, thank you.
Thank you very much. Yeah, thank you. The question is, okay, here's some very mathy definition of Ising model. Why did I even talk about it? Well, what I wish to tell you is that we can actually teach such a definition to our computers. Okay, and that's what we care about. We want to obtain a number, then we better be able to teach our computer about it. And the idea is that, computers take in only the variables. They do not know what measure is, but they know what moments of the measures are. So we are going to express DLR equation in terms of expectations, because this is what we can take as the variable. As we already saw in the case of the toy example, 5-4 theory in 0 plus 0 dimension. As I already explained to Raghu, consider this function is called indicator function. It indicates whether the spin is 1. And therefore, the corresponding expectation has the interpretation of probability that this spin is going to take value 1. You can now generalize this into, generic configurations. And the conditional probability is simply an idea that, we take the probability the nearest neighbors take value uj, and then we take the expectation for nearest neighbors taking the same thing, but on top of that, we are going to also specify the center spin assignment being ui. Okay, so this left-hand side is nothing but the conditional probability that we just discussed, and the right-hand side is exactly the same expression as before. Okay, is that this ui and uj are some fixed numbers plus minus 1. This is something that should hold for any fixed plus minus 1. But once you are given a choice of ui and uj's, this is just a number, and this actually gives linear constraints, okay, linear relations between different expectations. And now it sounds much like the toy example that we discussed. Okay? Of course, you might ask, where is the positivity? Well, we have a positive measure, and that provides positivity. So again, this is generic indicator function, and the corresponding expectation has a meaning of probability, so the probability should be positive. So this is a linear inequality, okay? And we saw that DLR equation was linear equations among different expectations. And there are other things that you can impose, things like, symmetry. And all of these things take linear form, okay? They're all linear in expectations. Now the question is, subject to all these constraints, we want to maximize or minimize some expectation value of interest. It could be, say, nearest neighbor correlator or magnetization. And this problem is something called linear programming, because everything is linear. Okay. This is the generic form. X is the variable, and A, B, C are some constants given. And this is even easier than SDP that I already introduced to you. And the corresponding min and max that you're going to obtain provide, again, rigorous bounds on the exact answer. So, any question on this? I hope that, this is where our previous experience with the toy example becomes very useful. This is very much analogous. It's actually even simpler.
So I have one question, if you don't mind.
Yes, please.
The Schwinger-Dyson equation in general does not imply a linear relation.
That is right.
Yeah. So how would you? I mean, in this case, it's just happens to be like that. So
You're
what
absolutely
do you
right.
do if
Actually,
it's nonlinear?
in our second example, which is large and matrix quantum mechanics, we know
Yes.
that large and factorization gives rise to nonlinear relations between double traces and single traces.
Yes.
In that case, actually, there exists a convex relaxation technique. So you can introduce new variables. So this is the cost that you have to pay. But by introducing new variables, you can actually make a convex relaxation of such non-linear relations. So that is, for example, an idea which was tested by Vladimir Kozakov and Duchan Zheng in recent years, but in the context of lattice gauge theory bootstrap. So there actually exists convex relaxation of those things.
I see. I mean, it's surprising because even in large n limit, the Schwinger-Dyson equations for gauge theories are not linear. Actually, there's a linear operator on a loop, but
You're
the right
absolutely right.
side is very complicated. I know that actually. So
Yeah, you're absolutely right.
yeah.
I mean, yeah,
Okay.
you are the expert, of course. But yeah, one thing I wish to tell you is that you can actually, so it's not an exact rewriting, but you can actually come up with a convex relaxation. It's a relaxation. It's actually a
I see.
weaker condition than the
I see.
nonlinear equality, but you can still impose it at the level of the convex optimization. And that's
I see.
exactly what people have been using in recent years
I
in
see.
Bootstrap.
Thank you. Thank you.
Thank you. Good thing is that actually in StemMax system, classical StemMax system, things are linear. Okay. So let me give you some example. This is 2D case. This is the critical value, so zero external magnetic field and critical temperature. This is the exactly known answer for the nearest neighbor correlator. And if you actually impose the bootstrap constraints, which are supported on some finite sublattice, I'm going to call it D3. It's like 3-size diamond. Then you're going to obtain this type of lower bound and upper bound, which are consistent with the exactly known answer. Okay. By the way, I wish to emphasize that these bounds apply to infinite lattice Gibbs measure. Okay, it's not a result for this finite thing. We are just imposing, again, part of the defining properties of the infinite Gibbs measure. But the result is rigorous for infinite Gibbs measure. Of course, you might complain that these numbers do not look too impressive. Wait a bit, I'm going to soon show you very impressive results. But there is one theoretical result, which I proved with math physicist, probabilist Shin-san. The theorem is like the following. So as you actually increase the size of this diamond over which you are imposing the bootstrap constraints, actually this bound is going to converge to a physical value of a Gibbs measure. Okay, so this is a convergence proof. Okay, actually this type of convergence proof in optimization literature is more generally known as Lasser hierarchy. And there is a very nice implication of this. What it implies is that Bootstrap, okay, this Bootstrap formulation of Ising model actually provides a very practical definition of the Ising model. Okay, it's just another way to write down Ising model, but it's a definition which you can teach to your computer, and your computer will happily spit out these type of numbers for you. Okay.
Can I just ask a question?
Yes, please.
No, I mean this is nice, but what is the practical utility of this of this definition? I mean, like we can get a number, we can put a partition function, we can put a Hamiltonian into a computer, and we can calculate all the properties of the Ising model in that way.
Yeah.
So
Good question.
so what does the
Right. So there is actually a practicality question, okay, which is that, okay, if you actually want to get the idea about Ising model, what is the most popular way? We typically learn Monte Carlo simulation, for example. It's on a large lattice, say some 100 size, and we are going to do some million times of sweeps to obtain some number. But that thing at best is giving you some number which is subject to statistical error of the stochastic processes. So the question is, if you want to actually ask, okay, how do I pin down some type of correlator to say 10th digit or 15th digit? How do I even do that? Okay. There exists that practicality question. And I'm going to soon show you how Bootstrap can pin down some numbers to 15th digit.
Okay, so I mean, okay, so in some senses, you're saying it provides a more concrete definition, even.
That's right. And
Because,
also, all these results are rigorous. Again, it's not an
Mm.
approximation. It's not subject to any statistical error. It provides a rigorous way to get the idea of physical quantities.
Okay, okay, thanks.
Okay, thank you. Actually, one can add further bootstrap constraints. There actually exists a lot of inequalities in the case of Ising model. Well, one of the most famous one is reflection positivity. Because I'm running out of time, let me briefly tell you that this is just saying that if you have reflection positive configuration of the spin insertions, then the corresponding expectation takes the positive value. This is one way to write it. Actually, you can actually turn this into a matrix positivity, just like the toy example that we discussed before, where the matrix elements are actually linear in the spin expectations. Okay, so I'm being a bit fast here, but the upshot is that reflection positivity is another positivity that you can implement, and it's also convex, and it gives you now semi-definite programming problem, SDP. Okay, so once you add this,
Okay,
now I'm going to tell.
we have like at least an hour and a half, if not more. So we are flexible with the time. So please don't feel.
Okay. Thank you, Raghu. I thought that I'm given only an hour, but okay. Then let me actually jump into a bit more detail then. Okay. In 2D case, there are three types of reflections. One is diagonal, the other is vertical on-site, the other is vertical off-site. Okay. Turns out that in higher D, you still have these three types of reflections. And consider the half space, okay, H1 or H2 or H3. And you can consider generic spin configurations, okay, spin functions, which have support only over this half space. Okay, this S underbar A, where A is a sublattice, is simply product of all the spin variables in that sublattice. Okay? And then this Ti is some real thing. Okay, so you can consider this most generic linear combination of half spin configurations. So this A is sublattice on the half space. For example, for H3 is here. And this RA of O is simply reflected version of that. Okay, and the statement of reflection positivity, which is actually not hard to prove, is that if you consider all times its reflection image and take the expectation, that's actually positive. This holds for any of the three reflections. And this is equivalent to the matrix positivity, where the matrix element is defined in this manner. So, and then now this is just like the toy example that we discussed before, which takes the form of SDP. So it's something, again, that you can plug into computer and it can happily spit out answers for you. So first thing first, let's see how it reproduces the exactly known answer. So in D equals 2, when external magnetic field is turned off, there actually is this exactly known analytic answer. And this is for the nearest neighbor correlator, while this is for the magnetization. And the black line is the analytic result. And here you can see the famous phase transition of the 2D Ising model. So magnetization is 0, but then all of a sudden it can be non-zero past this point. And for the bootstrap constraints, we are going to consider those coming from only this small diamond and a little bit bigger diamond. And those are results from this. So this light gray is from D2, very small diamond, while this blue is from this a bit bigger diamond. And you can see that it converges pretty quickly to the exact answer. And here's another thing. You can see that it gives very nice results. Of course, exactly known thing is nice, but the ultimate goal of this thing is to produce new things, which we do.
Could you show the previous slide again?
Yeah.
So the what are these plots? If you look at the magnetization plot, saying that the these empty circles are the upper bound and the purple are the lower bound, or?
Oh, sorry. Sorry. Thank you very much for the question. I should have been slower. So Gibbs measure, the number of Gibbs measure past this criticality is actually infinite. So actually, if you consider lower bound, it's going to be Z2 symmetric image of this. Okay, it's because anything in this middle is allowed. Okay, you can find corresponding Gibbs measures. So for that reason, what I plotted here is just the upper bound. Okay, so this is upper bound from D2. This is upper bound from D3. Did that answer your question?
And in the other plot, you really had both shoes. You were showing both the upper bound and the lower bound.
That is because this is Z2 symmetric quantity, while this is Z2 odd quantity. That's the reason why.
The lower
That's the reason why.
the upper bound.
Sorry?
In the right figure, you're saying the lower bound is just negative of the upper bound.
It is right.
Okay.
Yeah. Essentially due to the Z2 oddness of this property, this quantity. Thank you very much. Okay. So let's go to the case where basically nothing is known analytically. This corresponds to non-zero magnetic field. Even in 2D, for non-zero magnetic field, there's nothing known analytically. But Bootstrap is Bootstrap, we can still apply it. This is the result for nearest neighbor correlator. The upper bound is given by this colored thing, while lower bound is given by this grid that you can see. But they become highly indistinguishable in the intermediate region. And that's the reason why we colored everything. So the color is there to stand for the difference between upper and lower bounds. Okay. So for example, when it's around this red or orange, the difference is about 10 to the minus 3. Around yellow, the difference between the two is about 10 to the minus 6. In this blue region, the difference between them is like 10 to the minus 15 or below. Okay. So what I'm presenting here is that Bootstrap actually pins down, for example, here, your answer to say 10th digit or beyond. Okay? And here we just use Bootstrap constraint coming just from, very small size diamond. So this is a response to the question that I received earlier. Typically, if you want to compare this type of thing with the traditional numerics, you're going to compare it against Monte Carlo simulation. But actually, some of these Bootstrap bounds completely rules out the entire 1 sigma error bar of the Monte Carlo result. It's just because this is pinning down the result to very high precision, while Monte Carlo typically is good up to 4th or 5th digit. Good. And you can do the same thing for 3D. Even at zero magnetic field, there is no analytically known answer, and this is some preliminary result. This red line is the result of Monte Carlo, and this blue is the strongest Bootstrap bound that we obtained, and they are nicely compatible with each other. I think now we are ready to jump into the next topic, which is quantum mechanics at finite temperature, unless there is a question.
Yeah, I don't want to belabor the point too much, but you get great precision with Bootstrap, but how do you know that that captures the real dynamics of the system? Because you don't have any way to confirm that accurate result numerically using the exact partition function or Monte Carlo methods.
No. Again, what I'm telling you is rather the opposite. This is rigorous result. Okay, there is no reason to test this. This is just absolutely true. Bootstrap results are rigorous. It's just based on the very definition of the system. Sorry, did you say something?
No, I'm just because it seems to me that you have a set of constraints and you're trying to optimize the system so that it satisfies these constraints. And what you're saying is that these constraints rigorously capture the full dynamics of the system.
Well, there are two things. First is that these numbers are rigorous. That much is true. It's just because we are imposing what must be true. That's the Bootstrap philosophy. Of course, if you want to capture the entire thing, then you have to a priori impose all the infinitely many constraints. Here I'm imposing only a finite subset of all those infinite constraints. The reason is because I cannot plug all the infinity of the constraints into my computer. But good thing is that we have this convergence proof saying that if you actually systematically increase the number of the constraints that you are taking into account, then the answer is going to converge to the physical value.
Okay, I get it. Sorry, it took me a while, but I finally get it. Thanks.
Okay, thank you very much.
Because you have this convergence proof.
Thank you. Okay, now let's jump into quantum mechanics. Okay, we are going to have some Hilbert space curly H and a Hamiltonian plane H. Okay, and typically when we say system at finite temperature, at least when we have finite size Hilbert space, what we mean is that we have thermal density matrix which goes like e to the minus beta H. Okay, and the corresponding thermal expectation value is given by this type of trace expression. You might say, what is the defining property of this thermal density matrix or thermal state? And it's the celebrated Kubo-Martin-Schwinger, in short, KMS condition. And it means that this type of relation should hold for any operator O1 and O2. And if you recall, this is just the translation along the Euclidean thermal circle, and it's basically specifying the periodicity of the Euclidean thermal circle. In particular, this thing also includes Schwinger-Dyson equation. Okay. Well, this is good. At first glance, you might think that, okay, this is linear relation among the moments, so we can run the same argument. Okay, life is not that simple. What's happening is that this is actually non-local expression in terms of the Euclidean time, and for that reason, this is very hard to implement in practice. So you might ask, is there some alternative computer-friendly formulation for thermal state? Turns out that this idea was already explored back in the 70s by math physicists Araki and Sewell. And it was actually recently revisited by Fauzi, and Scarlett. I'm going to call their work FFS. It appeared last year. Actually, it was a response to my work on the classical Ising. These are people in the optimization community, especially the author here, Hamza Fauzi, is one of my go-to talk to person whenever I have some results in the optimization. And that motivated these friends to come up with quantum generalization of the classical Ising bootstrap story. And then they realized that KMS condition is equivalent to what I'm going to call FFS. So here's an equivalent way of writing down KMS condition. First, we have to impose Schwinger-Dyson equation. Okay, it's linear in the expectation value. That is nice. The second ingredient is something new. This is called thermal inequalities. Okay, in short, TI. There appear three matrices A, B, and C is the one which carries this beta dependence. And this combination should be positive. You might ask, what are these A, B, and C? They are given here. So here, A is given by O dagger O type expression, B is given by O dagger, C is given by this expression involving Hamiltonian commutator. Okay, and OIs are basically bases of operators. Of course, in practice, when we are doing Bootstrap, we are going to only consider some finite subset of the entire basis. The upshot, I mean, if this seems too out of nowhere, the full derivation, of course, is present in these papers. It's a bit lengthy to reproduce. Let me give you some essential ideas. So here C, for example, at zero temperature, where beta is infinite, we are going to drop the second term, and C is the only thing that matters. And you might ask, what does C tell us? It just tells us that any local perturbation of the ground state, which is the dominating state in the zero temperature, is going to increase the energy. That's the very definition of ground state. If you give any local perturbation, it's going to increase the energy. And the second term involves log. So roughly, you might get the idea that this might have something to do with the entropy. And that is correct in some sense. The precise sense in which that is correct is written here. So you might notice that this is actually energy perturbation plus, if you multiply everything by temperature, it's like E plus T times S, and the variation of it should be positive. So it's basically saying that variation of the free energy should be positive. That's the heuristic idea. The full derivation of this thing being equivalent to KMS condition is quite lengthy. But I hope that at least you see the idea. And in addition, of course, we want to impose that this thermal density matrix is positive, which translates to this, O-degree O-type expression being positive. There is an issue though. So this is linear in the expectation values. This is linear in the expectation values. Unfortunately, this involves log. So this thermal inequality is an inequality involving log of matrices. So it's not something that falls under the, framework that we discussed so far. There are actually two ways forward. First is that it turns out that this space of A, B, and C satisfying this inequality is still convex. You can actually show that. It takes a bit of a derivation, but you can show that they actually form a convex cone. And using that idea, optimization friends have came up with direct way to run the convex optimization over this inequality. The second thing, which is more familiar to us by now, is that there actually exists a strict semi-definite programming relaxation of this logarithmic inequality. And this is due to, again, our friends in the optimization community. And let me give you some brief idea about what this relaxation is like. So you can consider log of x. This x is just one real variable for now. It actually has this integral representation, where f is this type of function. Okay? And if you consider this type of inequality, it turns out that that is equivalent to positive semi-definiteness of 2 by 2 matrix written like this one. Okay. So now the idea is that you are going to discretize this integral, okay, to approximate log. That thing I'm going to call Rm. So here, Wj are the weighting factors, and Tj's are basically the, discrete points which you are using to discretize this integral. And actually, there exists a specific choice for this weighting factor and the dividing factors. These are called nodes and weights. The specific thing that we are going to use is something called left Gauss-Radau quadrature of order m. Okay, don't worry too much about it. It's just a way to discretize this integral expression. But there's a very nice property of this specific way of discretizing the integral. It is that this approximation actually strictly upper bounds log of x over all positive x. Okay? And if you actually increase the number of the discretization points, it's going to give you better and better approximation to log. And it's actually going to converge in some sense. And you can do further.
In these formulas that you wrote, X can be a matrix or?
Oh, I'm going to soon tell you. So later we are going to promote this to the case where X is a positive Hermitian matrix. Yeah.
Right now you are
but for now, it's just one.
Variable.
Sorry?
Right now you are just, all these equations are for a real X.
That's right. Just one real variable X. Thank you for the question. You can do further, improvement on the approximation. The idea is that this relation is actually equality exactly at x equals to 1. Okay, both of them are 0. Meaning that if you actually bring the points closer to x equals to 1, you're going to get better and better approximation. So for example, you can, based on this idea, you can rescale the points so that you can actually bring the points closer to x equals to 1. In any case, the idea is that there is a systematic, improvement you can do for your approximation, all of which actually strictly upper bounds log of x. And this strict upper bound is important for Bootstrap. It's important in maintaining the rigor of the Bootstrap. Okay? It's not just an approximation. It's a strict upper bounding approximation. So this was the original thermal inequality. Once you promote this thing to a matrix logarithm, the analogous result still goes through. You can replace this log by this expression, this approximation. Of course, because this is now strictly upper bounding log, the analogous statement here is that this inequality is implied by the original thing. So in other words, this is relaxed thermal inequality. This is strict relaxation of the original thing. And that's how we are going to maintain the rigor of the bootstrap. And finally, what was the reason that we bothered about this approximation is just because we had semi-definite expression for the positivity or inequality involving log once we introduce this approximation. And once you work it out fully in detail, of course, we don't need to work it out, like optimization friends already worked it out. It turns out that this relaxed thermal inequality is equivalent to the existence of Hermitian matrices T and Z, such that this type of equalities between different matrices and the positive semi-definiteness of this type of block matrices hold true. Okay. So, I mean, this was a bit of math, but let me give you the punchline. The punchline simply is that you can relax log inequality for the matrices into the usual SDP type problem. Okay. Semi-definite programming. That was the essential idea. And with this, we can proceed now. So here's a summary. Thermal bootstrap for quantum mechanics, you can phrase it as a semi-definite programming problem. Of course, as I mentioned before, there is a direct convex optimization that you can do, but this is one alternative way to do it.
Sorry, Minjae, can I
We are
ask,
going to maximize.
you had defined only as a function of a single variable, right? Or could you go back to the definition of this RMK?
Yes.
So yeah, Rm of x was what?
It was given by some specific combination of this function at
This-
different points.
And then you're just you're applying it to a matrix, right? So Rm
That's
was
right.
now applied to a matrix.
That's right.
Okay.
Yeah. Yeah. I actually skipped various steps, but yeah. Just because it's not going to be pleasant to present all the details. But yeah, the idea is basically that I motivated by, considering only the one real variable, but there's a straightforward generalization to the matrix case.
Okay, thanks.
Yeah, thank you. So this is our problem. So we are going to maximize or minimize some specific thermal expectation subject to Schwinger-Dyson equation and the relaxed thermal inequality that I just introduced, and positivity of the thermal density matrix, and normalization. Okay, and this is SDP problem. Okay, it's not much different from the toy example that we initially discussed from the computer's perspective. Of course, there may be extra relations that you can impose, things like operator relations, such as canonical commutation. And the resulting min and max that you are going to obtain, again, this is the result of Bootstrap. We impose only the things which must be true, so they provide rigorous upper and lower bounds on the exact answer. So FFS, our optimization friends last year, applied this idea to quantum Ising spin chain, and they obtained pretty nice results. Our interest will be on the matrix quantum mechanics, but before jumping into that, we can test it for the single particle subject to this Hamiltonian. This is quartic potential with the kinetic term. And here I'm just, giving you the result. The result is that we have upper and lower bound on the energy expectation value as a function of temperature. Equivalent way to say this is that we are considering the derivative of the free energy in terms of beta, inverse temperature. And this is the SDP problem considering words up to length 10, words consisting of x and p. And this M and K were the labels which stand for the approximation scheme for the logarithm. But of course, this approximation is strict relaxation, so we still maintain the rigor of the bootstrap. So this red line is the result that one can obtain by explicitly solving the Schrödinger equation to first, 10 or 20 eigenstates, and then you can plot e to the minus beta h. While this black region is the strongest upper and lower bound that we could obtain at the cutoff on the word length being 10. Okay, so it's pretty nice. It's consistent. This was toy example. let's jump into our main example, which is ungauged large n matrix quantum mechanics. Okay? The degrees of freedom are n by n matrices, X and P, n by n matrices. And we are going to consider hooped large n expansion. Of course, we are going to consider only the planar physics today. And we know that this actually arranges into genus expansion. And generic expectation, as far as I believe, is that they are going to be dual to gravity or string theories. There's a famous example of C equals 1 string theory and many other cousins of it. And finite temperature states in the matrix quantum mechanics are expected to be dual to thermal backgrounds, for example, black holes. So that's the reason why this type of thermal states are interesting. Actually, Bootstrap has already been applied to this type of system, at least for the stationary states. But it doesn't actually specify the temperature, but it applies to all the stationary states, and it dates all the way back to Polchinski's work in 1999. And recently, it was revisited with more systematics by these people. But now the new contribution that we made was that we can employ FFS framework, the thermal bootstrap framework, to study large and matrix quantum mechanics at finite temperature. Okay. So let me give you the specific example that we have. We are going to consider one matrix quantum mechanics. It is this Hamiltonian. There is a quartic interaction term, and this G is the interaction coefficient. X and P are n by n traceless Hermitian matrices, so they satisfy this type of commutation relation. And as we know, there is this global UN symmetry, and typically what people consider is gauged version of it, which simply amounts to restricting the Hilbert space to the singlets. And in this case, this problem is actually completely solved. It's known to be describable in terms of non-interacting fermions at large n. Today, we are going to consider ungauged version of it. Okay. Now, in the ungauged case, you have to consider all possible representations. And for that reason, it's actually difficult to study away from low temperature or high temperature perturbation theory. But Bootstrap is Bootstrap. You can still apply Bootstrap, and we are going to see the results that are beyond what we can obtain from this guy. Okay. So for the Bootstrap setup, we are going to consider operator basis being wars consisting of X and P up to some length. And we are going to consider the correlators of two edge joints only. So generically, you have to consider all the multi-edge joint expectations and bootstrap constraints on them. We are going to simplify our life. We are going to only impose the constraints which are expressed in terms of the two edge joint correlators. Well, good thing is that we can do the representation theory analysis to reduce this thing down to invariant tensor structures. And in the end, the expectation values of interest will reduce to single trace expectation and double trace expectation. Okay. Positivity is what it is. Odega O, trace is positive. Relaxed thermal matrix, relaxed thermal inequalities can be written in this tensor decomposed form. We are going to just focus on 1, 2, and 2, 1 element here. And that thing, you just plug 1, 2, and 2, 1 into this equation, and you're going to arrive at this thing. And you can do the similar business for B and C matrices.
I have a question, if you don't mind.
Yes, please.
So this OAB that you have written in the second line, expectation value of OAB, O/CD, these operators are basically elements of the operator basis or some combinations, right?
That's right. Oh yeah, X or XP or X
Right.
squared P. Yeah.
So I have a question that at finite n, however large, at finite n, there are constraints amongst these operators, no? Or
That's right. You're absolutely right.
so how do you take that into account? That's the hard problem.
Oh, great question. Actually, if this is a relation which holds a finite n.
Okay. Okay.
Okay, this is exact relation that holds a finite n, and all the positivity, relaxed thermal inequality, Schwinger-Dyson equation, all of these things, you can write down the exact version for finite n.
Okay.
So actually, I didn't prepare the result for the finite n in the presentation today, But if you look into our paper, we also have bootstrap bounds for the finite n case.
Okay. Thank you.
Yeah, thank you. It's just that, for the large n case, we can just take n goes to infinity limit of all these expressions. And all those things are still going to make sense as a bootstrap constraint. And we are going to basically do the optimization procedure with all those constraints, which are written as a large n limit of all these things. Right? So these are the ingredients. So I didn't explain this. So we impose Stringer Dyson equation, and there's also, trace cyclicity, canonical commutation, reality, all these conditions, which are all linear in terms of these, multi-trace operators. So these are all linear. But as already mentioned during this talk, turns out that at large n, so let me first explain finite n. At finite n, all these things you can treat as independent variables. Okay, multi-traces, they are a priori independent of each other. And you just have these linear constraints on it. At large n, this type of thing actually factorizes into product of two single trace expectations. It turns out that at least up to, say, word length 10, if you use all these relations, you can actually get rid of all the multi-traces, except for, say, 3 or 4. Okay, I forgot the exact number, but it was something like of order 5. So you can use either the convex relaxation that I mentioned before, or you can just leave them as new variable. It doesn't hurt. It doesn't hurt the rigor of the bootstrap. And the later part, which is the simpler step, is what we actually took to simplify our life. Okay. So these are the ingredients for thermal bootstrap. This is straightforward to plug into computer now. And here are the results. Okay. So this G, again, was the interaction coefficient. At different G value, we are plotting the energy as a function of temperature. And this L stands for the cutoff on the length of the word. So here we had this operator basis. And, whenever we have length, 7 or more, for example, those are not considered in this one. So this black line is actually not a line. It's actually a region, okay, in this plot. It corresponds to the result coming from L equals to 10 cutoff. And you can hardly distinguish the difference between upper and lower bounds. So here it's almost pinned down. You can see that it's almost pinned down in other cases too. Okay. So I already referred to the analytic results. In the low temperature case, of course, at the leading order, the ground state energy dominates. But at the subleading order, it's dominated by the first gap, which is actually achieved by the edge-joint gap. And the edge-joint gap computation was done by these physicists in the 80s. So this is the low temperature expansion. In high temperature, there's a famous story of a path integral on the thermal circle. Basically, the Matsubara frequency is going to be diverging at high temperature limit other than the zero mode if you Fourier decompose modes on the thermal circle. So now the problem reduces to the ordinary zero-dimensional matrix integral. So this is the result where gamma is defined in this manner. So for example, at G equals to 50, you can compare bootstrap bounds. So again, this black line is not a line. It's bootstrap upper and lower bounds. It's just that they are so close to each other that you cannot distinguish that. Okay. Here we plotted the low temperature expansion. It's very good at low temperature, but starting from around here, it's not that good. And this is the high temperature expansion. Of course, in the end, it's going to converge to the bootstrap result. But you see, this is the very strongly interacting, and in the intermediate temperature region, neither low temperature or high temperature expansions are good. Actually, if you can of course go and include more and more corrections. Well, we actually tried it. It doesn't improve the agreements that much in the intermediate temperature region. And the reason is simply because we are in the intermediate temperature region, okay, while these are the low and high temperature expansions. So this is another place where you can see the power of the bootstrap. Okay, bootstrap basically pinned down the answer, even in a region where the usual analytic tools are not available. Okay, I mean, I shouldn't say not available, not precise enough, but bootstrap just pins down the answer. There's one more fun exercise that one can do. It is to consider negative value of the coupling. Okay, so this is how the potential is going to look like when you take negative G. It's unbounded potential, but as long as we are in this region, okay, this is negative, but it's bounded by this critical value. It turns out that there exists finite energy ground state at large n. The singlet picture, okay, the singlet is the case where you can describe things in terms of non-interacting fermion, is that you can actually fill up the fermion C, and it's not going to leak out. Now we can ask the following question. In this regime, given G, can a thermal state of a temperature E exist? Okay, now you are boiling this thing, and you are asking how much can I boil it so that I still maintain the stability? Okay. Answer is that given G in this regime, there actually exists something we are going to call critical temperature, such that thermal state exists only if you are below the critical temperature. Okay, so behind the critical temperature, there's not going to be any thermal state. So how do you actually find information about this type of thing? In practice, well, Bootstrap actually provides you a way to do that. So given G, we have STP formulation, which formulates all the Bootstrap constraints. And sometimes STP can tell you that, oh, your constraints are actually inconsistent with each other. It's like you are having inequality x being greater than 1, at the same time, x being less than 0. Then you know that it's infeasible. Okay? So your Bootstrap or STP can find infeasibility certificate at some specific temperature T. That's going to call it as TSDP. If that happens to be the case, then this TSDP provides a strict upper bound, rigorous upper bound on the critical temperature. Okay.
Sorry,
So Bootstrap
of this TC of G, what is happening? So you have a ground state, but finite temperature state does not exist.
That's right.
What really,
So,
I mean,
yeah, extreme example is where this you are at GC. That's the place where you actually filled up the Fermi C as much as possible. Okay. Now you are increasing the temperature, then this eigenvalue is directly going to flow up, leading to instability, and your thermal state is not going to exist.
is this saying that there are a finite number of states in the well, or what?
Also, good. I mean, thermal state is a state. Okay, I wouldn't say that there's like finitely many or infinitely many states. When you are discussing thermal state, it's given by a specific condition. Okay. I mean, of course. Again, in the extreme example of G equals to GC, if you are just interested in the pure state, that there exists only one stable state, which is the ground state. And that's given by all the fermions filling the Fermi level up to this well, top of the well.
I mean, and I mean, at finite n, this system will not even have a ground state, right? Like for negative
You're
G.
absolutely right. You're absolutely right. At finite n, there's going to be tunneling, and none of this will exist as a stationary state.
So now you're saying at infinite n, there are some kind of infinite lifetime states in this well, right?
That's right, because the tunneling probability is actually suppressed at large n.
Is suppressed. So then why does this finite temperature make it not exist anymore? I mean, if the tunneling was suppressed anyway.
So you could have asked the same question for even the pure state. So at the criticality, if you actually consider what would have been the first excited state, you're going to have more fermions above this energy level, and then it's going to simply go out of the well. That's the physical picture. Or in other words, if you go and try to solve the Schrodinger equation, you will find that there is no normalizable wave function. That's a simple way to say it.
Yeah, okay, no, above GC, I understand. I mean, below, if you go below GC, but okay, but you're just saying there's some extra tunneling due to finite temperature that.
Oh, it's not even tunneling. Basically, your energy level already spilled over the well. Okay, so this is again in the Yeah, this is again in the singlet fermion picture, which actually is not valid even for like, ungauged case, but let me still use it because it's good for illustration purpose. Exactly at GC, your ground state is going to be described by all the fermions occupying the levels, all the levels that you can possibly occupy within the well. Okay. Excited states are typically given by hole being here and particle being energy level higher than what you are currently occupying. But this thing has energy bigger than the height of the potential, meaning that it can now cause instability. That's the thing. The question is whether you can actually contain all these fermions inside the well or not. Is it going to spill over? And that spillover may actually happen if you're now boiling the system. Did I answer your question?
Yeah, thanks. That's good.
Thank you. Okay, so this is how Bootstrap is going to give rigorous bounds on the critical temperature. So here are some, results. So this is very close to the critical value of the coupling. Critical value of the coupling has extra digits beyond this one. Anyway, we get upper lower bounds on the energy expectation as a function of temperature. This orange dot is the low temperature expansion. The upshot is this red line. Okay, this red line is the temperature at which SDP actually finds bootstrap constraints to be infeasible, meaning that KMS condition is not obeyed, okay, at this temperature. So there is actually no thermal state above this temperature. And you can collect all of these things and get some nice plot. So as a function of G, so this is the critical G, I'm plotting the strict upper bound, the rigorous upper bound obtained by SDP on the critical temperature here. And of course, the expectation at the critical coupling is that the critical temperature should be 0. So far, so good. I think we have to conclude. So I hope that I conveyed you the idea that Bootstrap is a natural framework for thermal physics. Okay. Actually, finite temperature states are defined by convex conditions on the expectation values. And for that reason, we can actually teach our computers about these conditions via the tool of convex optimization. The obtained bounds are rigorous and sometimes highly precise. And convergence proofs exist. There are several things that directly relate to what we discussed today. Statistical Ising Bootstrap relied on locality. So you might ask, okay, how do we get information about long-range correlators? In principle, any long-range but finite distance correlators can be pinned down if you include more and more bootstrap constraints. But of course, in practice, that's going to be very, very costly. So the question is there actually a bootstrap reformulation of the bootstrap problem that we discussed today, which can specifically address long-range correlators? So that's for the future. And in the statistical Ising model, there were two positivities that we discussed. First was the positivity of the measure, and second was reflection positivity. Actually, it's very interesting that for the convergence of the bootstrap, we relied on positivity of the measure. Okay. But in Euclidean quantum field theory, we know that God-given positivity is reflection positivity. So there's a very nice contrast between the two. If you actually consider one-dimensional Ising model on the lattice, the usual statistical case, it turns out that these two are not implying each other at all. Okay. So there's a very interesting story going on between the two, which I still do not have a full understanding of. And you might say, okay, another way to simulate all of these things, one of the most traditional way is to use Monte Carlo simulation. And you might ask, is there any relation between Bootstrap and Monte Carlo? Turns out that Monte Carlo is in the end just a stochastic process. And stochastic process, one of the fundamental things that you are after is equilibrium measure. So it's again a measure problem. It has positivity property, and you have analog of Schwinger-Dyson equation, which is given by the equilibrium conditions. Okay, and actually you can bootstrap such stochastic process. So the end result is reported in my work last year. The end result is that Monte Carlo, if you consider the corresponding stochastic process, actually helps you make the bootstrap formulation more efficient. So this is rather the opposite of the image that you might have about, this paradigm of bootstrap and Monte Carlo being main competitors of each other. Okay, here, this is the case where they are actually helping each other. You can apply the same thermal bootstrap to quantum many-body case. Actually, FFS work, the optimization friends work last year was exactly about that. And currently with my wonderful collaborators, I'm working on a problem with some further ingredients. Hopefully this paper will come out in a month or two. We consider ungauged model, but we can also consider gauged large M matrix quantum mechanics, and that's going to be very interesting. And in particular, for such system, there actually exists plethora of finite temperature phase transition. This is one very well-known reference where such a thing is discussed. So it'll be great if we can see how Bootstrap recovers them and how Bootstrap can actually go beyond the standard, analytically approachable cases. And, this is a big goal in the future. If we can actually address thermodynamics of systems like BFSS, they will be fantastic. Let me give an even broader viewpoint. Ingredients of Bootstrap was really two things. First is positivity, and second is convex conditions. Actually, this complexity may not be true in some cases, but still, these are the ingredients. So you might say, okay, as long as my system has these type of constraints, then I can apply Bootstrap. Indeed, that turns out to be the case. It turns out that there are many, many applications. The first time that this type of idea was implemented in practice and had a major success was in the field of quantum chemistry. We all know what minus 13.6 electrovolt is the ground state energy for the hydrogen atom. And what quantum chemists were asking was, what is the analogous ground state energy if you have many, many electrons? It becomes a very tough problem to solve analytically, but quantum chemists actually found a way to formulate such a problem into a semi-definite program. And they obtained very nice results, which are in good agreement with the experiments. In recent years, our friends in the applied mathematics and mathematics realized that such bootstrap approach also works for dynamical systems and stochastic processes. They have established many beautiful works, many beautiful results, both numerically and theoretically. And there's also recent work by Zhichen Zhang and Vladimir Kazakov on lattice gauge theory, bootstrap. And also there's traditional by now standard conformal bootstrap and the S matrix bootstrap. But I think that the list will grow more and more. And here's a homework assignment for everyone here, which is that after my talk, you might try to see if the problem that you are currently facing actually has this type of ingredients. If that's the case, then you might have a chance of bootstrapping your problem. With that, let me end my presentation, and thank you very much for your attention.
Thank you for the nice talk. Do we have any questions?
Yeah, I have one question.
Yes, please.
Yeah, so this ungauged matrix model that you talked about, would you know whether it is a integrable Hamiltonian system, or because if you gauge it, then free fermions is integrable, but
That's right.
if you have all representations, I mean, it's like a Calogero type of complicated type of system.
You're absolutely right.
And do you know anything about the chaos, or if you want to describe a black hole in terms of the ungauged matrix model, it has to somehow exhibit some, chaotic behavior, right?
You're absolutely
What
right.
we learned,
You're absolutely right.
the SYK model last 10 years.
I mean,
So,
as far
do you
as
know
this simple, yeah, as far as this simple model is concerned, I don't think there is, this string black hole type transition. This, so let me point this to you. So first of all, we consider this example simply because there are not that many analytic tools to actually consider ungauged matrix model,
Yes.
especially if you consider the thermal case.
Yes. Yes.
Yeah, so that was the reason why we tried this. But as you can see in this plot, it doesn't employ any of the interesting Hagedorn type phase transition, right? So this is not going to actually manifest things like black hole.
No, I asked a more mathematical question, whether that system is an integrable system or not. It's a math question, basically, whether this Hamiltonian is integrable or not. I mean, that's all I asked, actually. If you know, it'll be good.
I mean, I don't know of a rigorous mathematical statement. That much I don't know. As far as I'm aware, the non-trivial result on this thing really came from this paper. They actually analyzed how to solve the adjoint sector, and even that was very tough. In the end, if you are considering any specific representation, it is possible to write down the Schrödinger equation. And I think it is possible to solve for the spectrum. I don't see anything going wrong with that. But it becomes very complicated very soon. Even the adjoint computation was something that was very tough. And actually, on top of that, there exists so okay, I don't know the answer to the integrability, but I'm just telling you how complicated this problem is. If you want to consider the finite temperature case, you actually either want to employ this type of computation or this type of computation. Both of them are very hard if you go to sufficiently high orders. Yeah, I mean, yeah, sorry, I don't have a concrete answer to the integrability question.
Okay.
But at least I wish to tell you that in practice, this is a problem which is very tough to solve.
Thank you. Thank you
But
very
again,
much.
thank you. But again, that makes Bootstrap non-trivial because Bootstrap, you just teach your computer about this and then it's going to spit out very nice result like this.
Okay. Thank you very much for a very nice talk.
Thank you. Thank you very much.
Okay. Hello, can you hear me?
Yes. Yes, I can.
Yeah. So I had a question about, this comment that you made at the very end about, let's say, lattice gauge theory and so on. Like, if you want to set up such a bootstrap, like what would be the observables? So here in the quantum mechanics, you're just looking at this expectation values at finite temperature and so on. Like, would you look at some plaquette or something, that expectation value?
Yes, right.
And then.
Yes. Oh, indeed. This is the work of Vladimir Koskov and Zhichan Zhang, and they considered Wilson loop expectations, basically the plaquette and different types of loop expectation value. And then what they are imposing is the reflection positivity of open loops. You can consider different linear combination of open loops, and then if you take O there or O type expression, you have the positivity constraints.
So that is susceptible to some kind of. So you can write it as a semi-definite programming kind of a problem. Is that the point?
Yes. Yes.
That's a way to write it. Is that the statement?
Yeah. So the statement is that there's positivity, which takes usually STP form, and there's actually loop equation. Loop equation is linear if you're considering finite n, and you consider all the multi-matrices matrix expectations to be independent. But it actually becomes nonlinear if you consider the large n factorization. But then this gentleman employed convex relaxation of those quadratic equalities. And then that actually led them to find a way to formulate everything in terms of SDP. So the upshot is that you can still put this on, phrase this as a SDP problem, and you're going to obtain rigorous upper and lower bounds on things like plaquette expectation.
Sorry, on plaquette expectation. Okay. Yes. But I mean, this is also a broader question about this problem also, like how good can you calculate, let's say, correlation functions, equilibrium correlation functions, like in this lattice gauge theory, like so it's like there's a expectation value of a plaquette, but can you also like look at plaquette correlation functions and that kind of things? Or like, can you actually measure the spectrum, QCD spectrum That's the kind of thing that.
Very good question. First of all, I didn't write this paper, so I shouldn't comment too much about it.
Yeah.
But
So
if I'm aware, in some of their recent works, they actually come up with the estimate on the gap. And that is indeed obtained by placket type expectation. Actually, those type of correlators, placket, is something that is still part of the, SDP ingredients. Okay, you're not just considering only a single placket. Your loop equation and all of the positivity and so on are coming from generic types of the, loop configurations. So for that reason, you can, in principle, actually come up with a bound on placket type correlator. In practice, it becomes pretty expensive as soon as you're considering, bigger and bigger loops. But it's something that can be in principle done. I mean, I don't know all the details about lattice gauge theory bootstrap work that our friends have done, but that's the best I can tell you for now.
Ask a similar question about this ungauged matrix model itself that you're presenting. That, like, there, how far can you get the spectrum? Like, you have this energy, the expectation value of energy. That's a function of temperature. But like, if I wanted like the spectrum, okay, not the finite temperature, like how well can you do it? Like, can you get like?
Great question. So let me tell you. So actually, if you look at the low temperature expansion, you see the edge and gap. This is part of the spectrum, right? Actually, the computation of this is non-trivial. You have to solve something called long string wave equation.
Right.
And actually, what happens is that, because bootstrap bound is very tight and it agrees well with low temperature, if you actually do a fit of this thing to your bootstrap bounds, you can get estimate on this thing.
So that's like the first excited state about the gap, right? How that's the gap. But
that's right. That's right. Sorry?
Can you get the next one? Like the next?
I mean, if you actually have enough precision and if you know how to systematically compute all these, corrections, which are actually non-trivial, it includes like interactions between long strings and the contribution from the next excited states and all of those things. But in principle, if you have very good, bootstrap bound, then it's something that you can actually go and systematically extract. Of course, in practice, it requires your bootstrap bound to be very, very good. So I wouldn't commit to this thing in practice. But at least with our current bootstrap, we were able to recover this edge and gap very precisely.
Okay, thanks.
I just wanted to make a small historical point. So
yes,
this approach of using Schwinger-Dyson or loop equations with positivity was actually first done by Kurzinski and Anderson in a very important
You're
paper.
absolutely right. Yeah, I should have mentioned. I should have mentioned it. You're absolutely right.
Thank you.
Yeah, thank you. I should have mentioned it. Sorry. Yeah. Yeah,
Oh,
indeed.
the speaker.
Sorry.
No, we were just waiting for our turn. We are the Zoom people. So
please
go ahead and ask the question.
Yeah, I think Jyotirmaya was before me, if he's still there.
Hi, Minjae. Yeah, sorry. I have a couple of questions. It was really a very nice talk. I learned a lot.
Thank you very much.
So, the first thing is a little bit of a clarification. It's kind of a technical point. So all your plots seem to be against temperature, right? That's the variable you are using, like temperature, right? So, I mean, you might imagine using something like fugacity, like e⁻ beta, where you can get the whole range. Is there a technical reason why you're not doing that?
Technical reason is because we are the first person, like one of the first persons to do this even for temperature. Now, one can imagine extending this thing to, grand canonical ensemble. So here we just consider canonical ensemble.
Sorry, I don't think I got the point across. I'm sorry. So what I was asking, not the grand canonical ensemble, but just with use the variable e⁻ beta. Okay. I'm not introducing any chemical potential or anything like that, right?
Okay. Good.
Variable.
I see. Sorry.
Instead of T. Okay. So that will map the whole range of temperature to, 0 and 1, right? So, why are you not doing that?
Oh, no, I mean, it's not going to make much difference from the perspective of Bootstrap, you're just redefining your variable. You can, of course, carry out all this exercise in terms of fugacity, but it's just that in practice, there is no difference. If you're plugging this into computer, you're going to plug in one number, either for beta or e to the minus beta.
Yeah, but then that will capture, let's say, higher temperatures, more like, it'll completely, you don't have to truncate it at a particular T value, right? That's what I mean. Is there a technical problem of doing that? Like, so what you've done so far is like like I'm talking about computational challenge, like, so let's say I wanted to go to like 100, temperature T equal to 100. Okay. Would that be computationally more challenging than doing like temperature T equal to 1?
Great question. Actually, this is a great question. So if you look at thermal inequality here.
Yeah.
So if high temperature is when beta is nearly 0. You want to make sure that it's very tiny, but at the same time, it's non-zero. So say it's 10 to the minus 10, for example, then your computer should receive 10 to the minus 10 as some non-zero number.
Interesting, yeah.
This is computationally something that's going to cause either instability of your SDP formulation, if your SDP can recognize terms only up to, I don't know, like 7th or 8th digit. Or if you want to use high precision solver, it's going to cause more computational cost. It's something that can be in principle done, but it's going to be expensive. That's a very good point.
Yeah, okay. So, so this is what I was saying, that, if you use something like e to the minus beta, then you would need, all of it. But you're saying the inequality has beta in a way that makes it difficult for high temperatures to go to higher values. That's what you're saying.
That's right. You're absolutely right.
Great. Okay. So one more quick, thing. So about, let's say, using, let's say, the thing that you're calling thermal inequalities or this Araki inequality kind of things for the lattice. So you say there was a paper which did this, right? For
yes, right.
For the Ising model, for the quantum Ising model. So like, how does that compare with your technique that you presented initially? Like, is there a, is that better or worse? Can you comment on that very briefly?
Oh, actually, maybe I have given you a wrong impression. So we literally borrowed their computational framework to the finite temperature quantum mechanics, and we just applied it to different example. It's exactly the same type of the thing.
Yeah, but so are you saying that the initial description of the Ising model that you provided?
Sorry. You were comparing this quantum versus classical case.
Let's say we do it for the classical case also, using this inequality. Okay. So, I mean, would you consider that to be superior in some sense?
Actually, they are equivalent. There's a very famous theorem by none other than Araki and Sewell, telling you that KMS condition and the DLR equation that I presented to you are equivalent at the classical level. There's a very famous result. Yeah.
I see.
So they're actually equivalent, and that's the reason why optimization friends got actually motivated by my work, and then they considered the quantum generalization, which takes the form of KMS.
Okay. Thanks a lot. Thank you. This is really.
Thank you very much.
Yeah. Thank you. Yeah.
I really appreciate it.
Right. So I think, Takiro, you can go ahead.
Yes. So may I ask a question? I am Takiro Asma from Setsuan University, and thank you for your question. A very naive question is that, so whether we can detect the confinement, deconfinement transitions through the bootstrap techniques in the finite temperature system.
Great question. So that's actually what I alluded to in the this last slide. So actually, such finite temperature phase transition we know exists in many gauged large matrix quantum mechanics. For example, the simplest example is you take two harmonic oscillators. Okay, these are still large, but two harmonic oscillators which are not coupled to each other other than the gauging. Even in that case, there actually exists Hagedorn phase transition.
Yes.
Yeah.
Can it be detected by the bootstrap?
That's what we are currently. That actually was one of our initial motivation, and it's something that we hope to address. I mean, I shouldn't say like we addressed it because we didn't completely formulate it yet, but that's what we hope to address. Yeah, I mean, yeah, I cannot give you like definite answer to this question because we didn't try it. But at least Bootstrap framework, we do not see why it cannot be applied to the case where we have phase transition, finite temperature phase transition. But at the same time, we didn't produce any result on such cases yet, so I cannot commit to any answer.
Thank you very much.
Thank you.
All right. I have one last question, if there is still time.
Yes, please.
So first of all, Minjae, thank you for a very nice talk.
Thank you very much.
My question is that can you cast general relativity in the language of Bootstrap? Has anybody like thought about something like that? Because I know you do, they do it for field theory. So
great question.
okay, so I mean, if you don't know that, I mean, maybe nobody's done that. So I guess my second
there are several answers that I can give to you. So for example, you can ask, okay, GR, or say you start with some low energy Einstein Hilbert action. Okay, you can ask what are the possible high energy correction that you can have. Actually, this is something that people have already bootstrapped based on the fundamental principles like unitarity and so on. People actually came up with rigorous bounds on the Wilson coefficient.
But I think that's at the level of perturbative general relativity, right? I mean, just treating the graviton as another field. So, okay.
You're absolutely right. So, but another answer, so that's the reason why I told you that I can give you several answers. Another answer is that, for example, you can consider, full quantum gravity in 8s5 cos s5, which you believe to be dual to n equals 4 superambient. And people actually, in the works by people like, Shai Chester, Silvio Pupo, and, Yifan Wang, and many others, in recent years, they have very impressive results on bootstrapping n equals 4 superambient. And those are fully non-perturbative. You can do this bootstrap at any value of the, complexified Yang-Mills coupling. And
yes,
if we believe.
Yeah, no, I mean, I'm aware of those results. My question was from a different perspective, a different framework, because I want to ask: is bootstrapping a different way of doing physics? Is it in the sense that you have Lagrangian framework, you have a Hamiltonian framework? Can you think of bootstrapping as a framework on its own, or do you think it's just a technique like Monte Carlo? That's my question.
It's a very good question. I mean, I would say it's more than a technique. Sometimes, I mean, okay, at least for the GR case, my answer is that I have not thought about this question. And I'm not aware if there is such a formulation yet appeared in the literature. But, in all these cases that I've described today, you saw that Bootstrap is simply an alternative definition. Okay, it's not even like some way to formulate the system. It's just literally a definition of your system. Okay, so what I want to say is that there are cases where your physics of interest can be simply equivalently phrased in terms of some bootstrap problem. And in such cases, this is more than just a technique. It's just literally the physics itself. And I think for that reason, the mathematical theorem regarding the convergence of bootstrap actually has significant implication. Okay, it's not just some mathematical theorem. It's really telling you that you have an equivalent definition of your system. In other cases where you have some other working definition of your theory, but you are not sure whether Bootstrap is enough to give the complete details, I don't have good answer. Like maybe it's not good at capturing the full physics. It's just an alternative way to get some estimate of the things. I think it's really case by case. Yeah, I think that's the best answer that I can give to you for now.
Okay, thanks. It's better to be safe, I guess. So.
Thank you very much.
Okay, I think we've had a lot of questions. Let's thank Minjae again.
Thank you very much.
Yeah.
Thanks, Minjae, and thanks for doing this so early. You're up at 5 or something, or even before.
My pleasure. Thank you very much, Raghu.
Bye.
Bye.